Check one, check two. Hey! What's up, everybody? It is Mr. Boylan, and today in this video, we are going to interpret acid-base titration data. As always, taking a couple minutes to break it down, first we're going to describe an acid-base titration lab setup. What the heck is an acid-base titration going to look like in the lab? Number 2, we are going to define the equivalence point and endpoint as they apply to titrations. What are those things? What do they mean when we're talking about titrations? Numero 3, interpret acid-base titration curves to explain the relative concentrations of each species along the curve. So we're going to look at some curves and talk about what the heck is present along that curve. Number 4, we are going to compare and contrast strong acid, strong base, and weak acid, strong base titration curves. Okay, so first things first, what the heck is an acid-base titration? What is it going to look like in the lab? Recognize that in an acid-base titration, we're going to take one of those, an acid or a base, with a concentration that we know, and mix it with the other with a concentration that we don't know. Then we just take the known solution and slowly add it to the unknown while we carefully monitor the pH. So as you take a look at the animation on your screen, essentially this is what a titration is all about. We have a titrant of known concentration that we very carefully measure the volume that we dispense into the analyte of unknown concentration. As we do that, we are measuring our volume and monitoring what happens to the pH as we add that volume. Generally, burette. In the burette, we generally know the concentration of the substance in the burette. And then in a beaker or a flask, we have our unknown solution. In general, we have that connected to some sort of pH probe, which is connected to some sort of monitoring system. It can let us know what's going on with the changes in pH. This is a little old school with this giant computer. Now you can just monitor it using your cell phone. Technology. Bottom line, this is what a titration looks like. Now, your first important vocabulary word here is what's called the equivalence point. This is the point in the titration when the number of moles of base is stoichiometrically equal to the number of moles of acid. At that point, your titration is complete. So let's take a look at a couple of acid-base neutralization reactions. These are the types of reactions that you're going to perform in its acid-base titration. And when you reach the equivalence point, you have reacted the stoichiometric ratio of acid to base. Many times it's a 1-to-1 ratio, but be careful because occasionally it's 2-to-1, especially when you have those hydroxides with those group 2 metals. Cuidado! Woo! Alright, so before we get too confused, let me work through a titration to help you better understand what's going on. In the example titration that we're working with, I've got my burette, and it's initially loaded with 50 milliliters of 0.1 molar sodium hydroxide. That's my titrant, my known concentration. Down here in my Erlenmeyer flask, I initially have 10 milliliters of hydrochloric acid. I don't know the concentration, I just know that I have 10 milliliters of it. That's my analyte. That's what I'm analyzing. We're going to try and figure out what is the concentration of this hydrochloric acid. Couple things to note before we start. This is a strong acid and a strong base. So as we look at our key here and notice what's happening in both our burette and our flask, because they're both strong acid and a strong base, they are completely ionized in each of their separate containers. Now, as this titration proceeds, I'm going to reference this titration curve that corresponds to this titration. Now, the curve has already been completed to help you understand what's going on, but I'm going to highlight the points along the curve as we reach them. Now, initially, my acid solution has a pH of 1, which makes sense. Acidic solutions have pHs less than 7. Now, I'm going to start dropping in the base. Okay, so I'm going to drop in a sodium hydroxide. Boop. And I want you to think about what's going to happen. It's a neutralization reaction. The hydrogen ion from the acid is going to react with the hydroxide ion from the base that I just dropped into solution. When the hydrogen ion reacts with the hydroxide ion, they form water. Neutralize. Notice that I also drop in some sodium ion, which is just a spectator ion in this reaction. I'm going to continue to drop in the base. Boop, 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 boop. Alright, at this point, I've added 10 milliliters of my sodium hydroxide solution. Take a close look at my analyte. Recognize that I have reacted a bunch of the hydrogen ions with the hydroxide ions that I've dropped in. However, I still have several unreacted hydrogen ions in solution, so this titration is not yet complete. So I'm going to drop in some more. Now I've dropped in 20 milliliters of my base. And notice I have a huge jump in pH. I go from this distinctly acidic range up to neutral. As you take a look at my analyte, notice that I've used up all of my acid. It's reacted with the hydroxide that I've dropped into that solution. So all that's in solution at this point is water and my aqueous sodium chloride salt. Now you can imagine how the equivalence point would be important for some stoichiometry. If I'm using a 0.10 molar sodium hydroxide solution and I used 20 milliliters, 0.020 liters to reach the equivalence point, I can then figure out how many moles of sodium hydroxide were required to react all of the acid in my flask. In other words, I reacted 0.0020 moles of sodium hydroxide. And think about the relationship that exists in my balanced chemical equation. If I reacted 0.0020 moles of NaOH, I also know that I reacted the same number of moles of HCl because my ratio of HCl to sodium hydroxide is 1:1. And if I know that that 0.0020 moles of HCl was originally in 10 milliliters of HCl, or 0.010 liters, I can determine that the concentration of my original acid solution was 0.20 molar. Boom. And that makes a lot of sense. I needed 20 milliliters of my 0.1 molar sodium hydroxide solution to react completely with 10 milliliters of a 0.2 molar solution. Take some time to think about that, because it's an important concept. Boop, 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 boop. All right, now once we keep going, I've added 10 additional milliliters to my analyte. Again, we have a huge jump in pH, and this time it's because the hydroxide ions that I've added have no acid, no hydrogen ions to react with. And so it's just a buildup of hydroxide ions, and so our pH jumps way up here to the basic range. Last couple of things here with titrations. It's important to recognize that we're not always going to monitor the pH throughout the titration. Many times we're just looking for the amount of acid or base required to reach the equivalence point. So often we will use an indicator whose color depends on the pH and can be used to monitor the pH during a titration. Now, the point where the indicator changes color is called the end point. And ideally, you choose an indicator whose endpoint, or the point at which the color change occurs, happens at approximately the same pH that the equivalence point will occur. This way you can determine the stoichiometric relationship visually by observing that color change. And again, there's a whole host of acid-base indicators. We've used a couple of these already, like bromthymol blue, each of which change color along a different pH range, and will be selected depending on the type of acid-base titration that you're working with. The important thing to recognize, though, is that you want that color change to happen at approximately the pH of your equivalence point. Okay, last couple of things to think about here as you think about titrations. Keep in mind that titrations involving a strong acid and a strong base will have an equivalence point at pH of 7. This happens because the salt that forms during the neutralization reaction is a neutral salt. So here's an example of a titration curve of a strong acid and a strong base. clearly indicated because our equivalence point occurs at pH of 7. Keep in mind that you can also do the reverse. You can titrate a base with an acid. Simply recognize that your titration curve will be flipped. You'll start with a basic pH and end up in an acidic range. But once again, if it's strong acid and strong base, the equivalence point will occur at pH of 7. However, you want to keep in mind when you're working with weak acids and weak bases, and you're titrating them with a strong counterpart, your equivalence point is not going to occur at pH of 7. And again, that's because the salt that forms can either be acidic or basic, creating additional hydronium or hydroxide ions at the equivalence point. So in the example of a weak acid and strong base, your equivalence point is going to have a pH greater than 7. And this is because the salt that forms is a basic salt, creating additional hydroxide ions at the equivalence point. Here's an example of a weak acid, strong base titration. Notice your equivalence point is not at pH 7, but is in the basic range. Conversely then, if you're doing a weak base and a strong acid, recognize that your pH will be less than 7 because the salt formed during the neutralization reaction is an acidic salt. Boom, here's an example of a titration curve that's weak base, strong acid. Once again, notice your equivalence point is not at that neutral pH 7 because the salt that forms is acidic. All right, and that does it for this video. Have a fantastic day.